In this lesson, you will learn how to work with rational exponents and radicals. Let's first look at the rules. If you have a power, a raised to the fractional or rational exponent 1 over n, that's going to be equal to the nth root, and then your base becomes your radicand. So the denominator of that fractional exponent becomes your index number. Let's look at a to the m over n. Notice in this one, our base is still inside the radical, so it becomes our radicand. The denominator is your index number, but the numerator is going to be your exponent. So I always say if it's up high, it stays up high. So if it's up high in the fractional exponent, it's going to stay up high as an exponent in the radical form. You could also write it, again, with the n as your index number, but where the m is inside the radical on that radicand. They are equivalent. Either way would be fine. Let's look at some examples. First, we're going to change to radical form. So if we have the fractional exponent or the rational exponent, we can change that to a radical form. So let's look at 144 raised to the 1/2 power. So if we have our power, our base number is inside the radical. So 144 is inside that radical. And then the denominator of our fractional exponent is our index number. The numerator is your exponent. So you could put a 1 here, but an exponent of 1 is not necessary. Actually, if you'll notice, an index number of 2 is not necessary. So really the simplest way to write this is just the square root of 144. So 144 raised to the 1/2 power is the same as just the square root of 144. Let's look at example number 2. We have 32 raised to the 4/5 power. Again, let's rewrite that in radical form. So the 32 will be our radicand inside the radical sign. So our fractional exponent is going to make our index number and our exponent on this radical. Well, if it's up high, it stays up high. So that 4, because it's in the top of that fractional exponent, it's going to be our exponent on this radical. So you can put it outside the radical, or we'll rewrite it and also show it on the inside. That means this denominator is our index number. And I actually visualize, if it's here in the denominator, I visualize it jumping into that index spot. So let's rewrite that 4 could go inside the radical. So the 32 can be raised to the 4th power, but then we still need our index number of a 5. Those numbers could not be understood numbers. They would have to be shown. Let's look at changing to the rational exponent form or fractional exponent form. So change to rational exponent. So let's look at example number 3. This time we have the cube root of 1,331. So let's change this from a radical to the fractional exponent. So 1,331, that's our base number. And then we'll make our fraction based on our index and exponent on the radical. So our 3 is our index number. I visualize it jumps right into that denominator spot. Your exponent, if it's up high, it's going to stay up high in the numerator of that fractional exponent. So we imagine, or not imagine, there is an exponent here, but it's an understood 1. So that's what we have as our numerator of our fractional exponent. Let's take a look at number 4. Here we have the cube root of 8, and all of that is raised to the 4th power. So rewriting, we have our 8 as our base. We're going to make our fractional exponent from the index and the exponent on that radical. Well, starting here, if it's up high, it stays up high, so put the 4 in the top of that fractional exponent, and your index number is your base, or your index number is your denominator. So it is rewritten as 8 raised to the 4/3. Let's look at one more of this type. We have the square root of 81, and that is raised to the 5th power. So let's put our 81 as our base, and we want to set up our fraction bar for our exponent. Well, notice here, because we don't see an index number, it is a understood 2. For that square root symbol, we actually have an index number of a 2. So with that index number, it becomes our denominator of our fractional exponent. And the 5, because it's up high, it stays up high as the numerator. So we have 81 raised to the 5/2. Now let's look at actually simplifying some problems. So example number 6. We have 81 raised to the 1/2 power. We're going to add that with 49 raised to the 3/2 power. We're going to first start by rewriting these fractional exponents into radicals, because we can actually simplify radicals in our work. So the 81 inside of the radical, the 1 is our exponent number on that radical, so you can put it there or not, it wouldn't matter. The 2 is going to be our index number on our radical, so again, you can put it there or not. I actually prefer showing that index number and exponent even if it's not required. That way I know I've accounted for each part of the problem. Let's look at the other part. We have our 49 inside of our radical. The 3/2 will make our index number and our exponent. So the 3 will be our exponent. That 2 is our index. And we wouldn't have to put that 2 there. It just helps me know I've accounted for each part. So let's simplify. We can take the square root of 81 as well as taking the square root of 49. You should know those as perfect squares. However, you could go over to the side and do your prime factorization. So 3 goes into 81, 3 goes into 27, 3 goes into 9, and of course 3 goes into itself. So because we have an index number of a 2, we're going to be looking for pairs of like factors. So 3 times 3 gives us a 9. So again, you should know that the square root of 81 is 9 because that is a perfect square, but it still works if you need to show the prime factorization. Let's do the same for 49. You can divide that by 7, and then another 7, and we do get a pair of 7s. So of course we bring that down for the square root of 49. But notice here, we've not used our exponent to the 3rd power. Make sure you bring that down in your work. We don't necessarily need the exponent on the 9 because it was a 1. So 9 to the 1st is still going to be 9. But we definitely will need this 7 raised to the 3rd power, which we will actually do next. We will do exponents before we add, following order of operations. 7 to the 3rd, we found that is 349, and then we'll add to finish up this work. 9 plus 349 gives us 352. So in this problem, it was helpful to change those fractional exponents to radicals so that we could simplify. Let's take a look at number 7. Here we're going to have n to the 4th, and we're going to raise that to the 3/2 power. Well, when I first see this problem, I actually notice an exponent property. So let's go back and recall our exponent property that says a to the m, and that's raised to the nth power. So power to power, you multiply. I stress the p's to help you remember the operation that we should do. Multiplication is the only one that has the p. So we add, subtract, multiply, or divide. If it's a power to power, you multiply, stressing those p's to help you. So let's do that. So we have n to the 4th raised to the 3/2. You will multiply 4 times 3/2. So you might need to come over to the side to remind yourself how to multiply fractions. So you can put that 4 over 1, and you could multiply straight across. So 4 times 3, 1 times 2, you'll get 12 over 2, which does reduce to just 6. Or when you're multiplying fractions, you can reduce in the diagonals. 2 will go into 4 2 times, and 2 will go into self once. And then we can multiply across. So 2 times 3 is 6, 1 times 1 is 1, and then of course that reduces to a 1. That reduces to a 6. So that's what I first noticed when looking at this problem is an exponent property. But you can also simplify this with radicals. So let's see it work that way. So we're restarting with the same problem. So either method is going to be fine here. So let's actually change what we have just learned, this 3/2 power, let's change that to a radical. So rewriting our problem, the n to the 4th goes inside the radical. Since it's our base on our power, it goes inside of our radical. So the 3/2, if it's up high, it stays up high. So the 3 is going to be our exponent. And that 2 is going to flip around and become our index number. And of course, as we've already mentioned, a 2 is not required to show as an index number. We can simplify this radical. N to the 4th, we're going to be looking for pairs. So let's write out those n's. 1, 2, 3, 4 of them. Don't drop your exponent. We haven't used it yet, so bring it on down. We do want pairs since we're doing square root. An index of 2 tells us to have pairs. So we have n squared, and all that is still raised to the 3rd power. So again, we'll still need that exponent property, power to power multiply, which gives us n to the 6, because 2 times 3 gives us a 6. So I know in this case, it looks like it takes more steps to simplify. However, if you don't recall how to multiply fractions, this might be a better method for you, even if it does require more steps. Let's look at one more example. Number 8. We have 27 p to the 6, and all of that is raised to the 5/3 power. So again, this is a problem I'm going to show you being worked 2 separate ways. And of course, you just pick the one that works best for you. So let's first start with what we've learned with this lesson, that fractional exponent change to the radical form. So let's rewrite. The 27p to the 6 would be inside that radical, changing the fractional exponent to our index and our exponent. So the 5 is our index, and 5 is our exponent, and 3 is our index. Use that thought of if it's up high, it stays up high. So if it's up high in that fractional exponent, that top number, the numerator, it stays up high as our exponent on the radical. So now we can take the cube root of 27p to the 6. You may know that 27 is actually a perfect cube. If not, just go over to the side and show your prime factorizations. So divide by 3, divide by 3, and finally another 3. So it says we need 3 of the same factors, and we happen to have 3 3's. You can also write out your 6p's. So 1, 2, 3, 4, 5, 6 p's, and then again group them in groups of 3. So that becomes 3p squared. But don't drop that exponent, we still need it to the 5th power. Until we use that exponent, we want to bring it down in each line of our work. So now we need to recall another exponent property. So this property we're going to use is going to be where we had things multiplied together, so a times b, and all of that's raised to the m power. Each factor gets that exponent. So we're going to use that one here at this step. So our 3 gets the 5th power, and the p squared gets the 5th power. So 3 to the 5th, p squared to the 5th. Well, 3 to the 5th power, you could use a calculator to calculate that. It does give us 243. And p squared to the 5th, we just used that property up in the previous example. If it's a power to power, you multiply. So here, multiplying those numbers, 2 times 5 gives us p to the 10th. So as I previously mentioned, we could work this in another way. So let's do that now. We have this time the same problem, 27p to the 6, and all that is raised to the 5/3 power. This time let's actually start by using that property that gives the 5/3 power to each thing. So the 27 is going to get the 5/3 power, and the p to the 6 is going to get the 5/3 power. So with the first part, we could rewrite that with our radical form. The 5 is our exponent number, the 3 is our index number, and of course 27 being the radicand. The p to the 6, we can multiply that 6 with the 5/3. So let's go off to the side and do that. 6 over 1 times 5/3. Again, you can multiply straight across and then reduce, or I prefer to reduce first. In the diagonals, I can reduce by 3. So 3 goes into itself once, 3 goes into 6 twice, and then multiply across. That gives us 10 over 1, or just 10. So multiplying 6 times 5/3 gives us p to the 10th, which is pretty good because in our previous example, our answer did have p to the 10th. So let's just work out this part to see if we can get it to equal the same as the previous example. So cube root of 27, we've actually already done that. We should know by now that that is 3. So that comes out as 3, and again, don't lose your exponent, so 3 to the 5th, and then of course bring down your p to the 10th. 3 to the 5th does equal 243. So our final answer is the same. Either method you see to work it, feel free to just use whatever works best for you.